Hey guys, this is me, Mr. Wei. I just want to finish up a few things on this section before moving on to the next section. Okay, so just as a reminder, I know some of the things I went over in class in my hour-long lecture. I do apologize. I totally kind of fumbled around. Okay, so let's go back really quick. Um, let's go back to the first derivative test. It says see if the slopes and derivatives around your endpoints are positive and negative. Let me see if I have that example. Oh, shoot. So if you remember here, so this is the example for the first derivative test that we did. We found the first derivative for, it was this problem right here. We found the first derivative, which is that. And then we set it equal to 0. We found the roots, -2 and 2. And then what we did was we just plugged in like a number. We plugged in, like let's say right here, we plugged in a number that was equal, like that's bigger than 2, let's say, to the right. I plugged it right into the first derivative. And then I found that it was a positive number. So I just put that it was positive, and that represents that just represents positive here. And over here, I took a number like in between -2 and 2, which I could use as 0. That would have been x equals 0. I took f prime of 0, which is 3 times 0 squared minus 12. That gave me -12. So that's a negative number. So I said that's just going to be negative. That's going to be, it's just going to be negative, and this is going to be positive again. So that tells me that if you have on the left side, your first derivative is going to be positive, and you take any of the first derivatives on this side, it's negative, then you have a local max, a local min. Okay, so we got that. Let's just reiterate, though, on the second derivative test, it's a little bit different the way I kind of worded it. Second derivative test was you find the second derivative, you find the zeros. So like at this point here, I had this equation. I found the first derivative, then I found the second derivative. I set it equal to 0, the second derivative. Then I got one point that could have been my point of inflection, right? And then the test was a little bit different. So for this test, I found that the possible point of inflection, it's not yet a point of inflection, is 7/3. But I decided to kind of write this a little bit differently, and I kind of wish I would have rewritten it the other way to make it easier. But I said, are the first derivative, this is first derivatives, okay? That's why I had this arrow. Are the first derivative slopes around the inflection points increasing or decreasing? Okay, and the reason why I did that, because I went through such a long time to talk to you guys about this diagram here. So here, I thought it was more intuitive to say, okay, the actual slopes, the first derivatives, if they are decreasing, right? They're really steep, and then they're decreasing over time. Okay, if the first derivative decreases, then that's concave down around this kind of possible point of inflection. I don't know yet. Okay, then I look at the first derivatives and see if they're increasing, and they were. That says that the first derivative is increasing. So to keep consistent with that logic, I found it useful to say, whoops, sorry. So again, I'm just kind of reviewing what we went over because it can be kind of confusing. The second derivative, I also asked you to tell you, like the first derivative, I asked you to just see just test the first derivatives and see if they're positive or negative for the first derivative test. But here on the second derivative test, I actually asked you to use the first derivatives again around the inflection points to see if they're increasing or decreasing. So how that would look is like this. After I found out my possible point of inflection, I make a number line with the point of inflection. On the left-hand side, I actually use not the second derivative, but the first derivative again. Only this time, I have to use at least 2 points. I used a number that is quite a bit smaller than 7/3. That's 0. And I got 22. And then I had to use another point here, that is like slightly bigger than 0, just to see what would happen if I increased it, but it has to be smaller than 7 over 3, to the left of 7 over 3. And I found that that was so this is what's really confusing, that is going to be equal to 0. Okay, so 22 to 0, seeing that that is a decrease in the first derivative, then I say that's concave down. Okay, and the same thing goes over here. I picked two numbers that are bigger than 7 over 3 and just saw sequentially from t to 3 and t equals 4, did it increase or decrease? Well, it increased in the first derivative. Then I said that's concave up. So that's really confusing. I think I just need to clarify, because in the first derivative test, I asked you to test the points on step 3. It says here on step 3 to just plug in the first derivative and see what the sign is. Okay, and that's it. If it's a negative sign, it's a positive sign, right? And over here, I asked you to use the first derivative again. Only this time, I want to see not if it's positive or negative, but if it's what is it? If it's increasing or decreasing. Well, just letting you know, you have another option to doing this, and I think I talked about it in class, but I really wanted to kind of show you formally what you could have done as well. Step 3 could have been written one more way, or step 3 could have been done in one more possible way. What I could have done is I could have used like some kind of point. I will use t is equal to 3, because that's bigger than 7 over 3, and t is equal to 0. I could have just used x double prime of 0, which x double prime of t is 12t minus 28. So this would be 12 times 0 minus 28. That would be negative 28. That's negative. I just go by the sign again. So that's negative. And then over here, I just go by the second derivative again. Put that in. That would have been 12 times 3 minus 28. That would have been positive. What is it? 36 minus. That would have been positive 8. So that tells me all the second derivatives over here on this side. And if you have, again, if you have decreasing or you have a negative value for the second derivative, then that would be concave down. You can look at it two different ways, and this would be concave up. And if you have concave down and concave up, that would give you this confirms that this is a point of inflection. Point of inflection, sorry. And also, I didn't go over how you would answer this. You would say that the interval of x is less than 7 over 3, not equal to, but just less than 7 over 3. You have concave down. And then the other interval, x is greater than 7 over 3, is concave up. And the point where it shifts concavity is what we call the point of inflection. Okay, so step 3 actually could have been, are the f double prime slopes around the inflection points positive or negative? So you could have done it that way too. Okay, so step 3, you have the option of saying step 3, this is an alternative step 3, is are the f double prime slopes around the possible inflection points. We don't want to say the actual inflection points, but possible inflection points, positive or negative. Okay. So this is an alternative. And for those of you, you can kind of fast forward this if you don't want to get confused, but for those of you that are trying to be inquisitive about this, technically, see if the slopes, the first derivatives, I'll say, the first derivatives. So this is from the first derivative test. We use the first derivative around your endpoints, critical points, or positive or negative, right? What was I going to say? If they are positive or they're negative, if you found, let's say instead of finding the first derivative here and then plugging it into, like, you remember I said find the first derivative and then just plug it in to see if the signs, if the signs are negative or positive. What you also could have done is you could have plugged in 0 back into the original function, but you had to do it twice and see if it's increasing or decreasing. If it's decreasing on this side, and then over here, you would have found out if you plugged in t equals 5, or you would have found 2 points that are bigger than 2 and then plugged it into the original function, saw if the slopes, or if those values were increasing, then you could have determined that this was a local minimum as well. But that's really complicated. So thinking back to it, I think the way I showed you is still a little confusing. It's in the steps and what the steps look like. But I think it makes more intuitive sense to understand it that way. But I'm just letting you know that there is an option here. And why do I keep saying a possible point of inflection? Well, there is a scenario where, let's take a look here. Look at this guy over here. You have 3 possible points of inflection. This one over here, I can tell this is concave up, and then it goes into a concave downward motion, right? And then over here again, this is a point of inflection as well. This is concave up, and then at this point of inflection, from this point on, this is concave down. However, this is also, if you plugged in, so let's just say this is f, this is the function of f right here. If you took f double prime, you would also find f double prime is equal to 0 right here as well. But look at both of the sides of this possible point of inflection. Here, it's going down. And then on the other right, the left-hand side of this possible point of inflection, you have concavity going down. And then on the right-hand side of this guy, you also have another scenario where the slope or the concavity is going down. So that ends up being, that is a critical value of f double prime equal to 0. When you set the second derivative equal to 0 and you're trying to find the values where the f double prime is equal to 0, right? This is you found 3 different points. 2 of them are possible points of, or 2 of them are actually points of inflection. This possible point of inflection ended up not being one because the concavity never actually changed, but yet f double prime was equal to 0. Remember, the second derivative is equal to 0, not just the first derivative, the second derivative. Okay, so that is a perfect example of something that is not an inflection point, but could have been an inflection point, but it just wasn't when we actually looked at it. Okay. All right, guys. I think that's about it. Yeah, that's all I really wanted to show you for now. Okay. And again, yeah, just more examples. Okay, guys. You guys have a grand day. Thank you guys so much for listening. And then I'm going to post some videos for the last section 5-4. Bye.